And one has to ask oneself the question, is this feasible, that dust eventually formed life, and life eventually formed the complex organisms and structures that we see in the world today? Is that feasible, all by itself, driven by a process which required natural selection? We'll be dealing with all of these issues. Now, science further teaches that once this process had started, then on our own planet, through various ages, which are characterized in millions of years, life came into existence, and the evolution of macroorganisms, that's everything that creeps and crawls and does whatever it does, took place in the last 600 million years. And there's a huge time scale which is thrust at us and say, there it is, you do with it whatever you deem fit. And then we are taught that since this early dawn of the macroorganisms, I'm not talking about the prebiotic world, the world can be divided basically into time zones, which geology has basically termed the Paleozoic, the Mesozoic, and the Cenozoic, and that in that time, organisms evolved, and that today we can actually see the record of this evolution in the rocks. That's the science of paleontology. The science of geology concerns itself with how the matter was formulated and formed on this earth, how it came into its present position, and how everything came to be as old and as distributed as it is today. Now, is this true? Do we have such a paleontological record? The answer is yes. Do we have such a geological record? Well, the answer is yes and no. Because nowhere in the world do we have such a complete record. We have a fragment here, we have a fragment there. So basically what we see on the left is a theory which science has put together. It is not based on a definite column that we can go and look at in any place of the world. So tonight I want to look at the basic assumptions of geology, just the basic assumptions. Tomorrow night we will be dealing with the living organisms. We'll be looking at how the organisms evolved, how the world tells us they came into being, and whether this is in line with what we see or whether it is not. These are very important questions so that people can make informed choices. Let's first have a look at some of the questions of age. Radiometric dating. Radiometric dating is a technique that is used to tell us how old objects are. And basically, it's not a very complex system, and it works very well. You can do it in a laboratory. There are ways of exactly determining the ratios of certain isotopes to each other, and this information is used to tell us how old things are. But the problem is, you have to make certain assumptions. And let's just run through them. The first assumption you have to make is that the rate of decay and half-lives have remained constant over time. Okay, basic principle. You have a specific rock. In that rock, you have elements which decay by radioactive decay. For example, uranium-lead dating, you have uranium, you have a certain time in which it decays to a certain isotope of lead, and after X millions of years, you have half the amount of uranium as you had before. Over the next same time period, again, you have, another loss of half the material. We call that a half-life. And so you can determine, by determining the ratio of the one to the other, how long this process has been going on. But you would have to know that the rate of decay and the half-lives have remained constant over time. And there is evidence that it has, and there is evidence that it has not. So both sides of the story can be found in the literature. The second principle is a very simple one. If I want to know how old something is, then I must be sure that the clock was set to 0 when the material was formed. All right, that's very simple. How do I know how old any one of you are? What basically do I have to know if I want to know how old any of you are? I must know when you were born. Isn't that right? I must know when you were born. So if I have a birth date, well, then I can work it out. This individual is X number of years old. How old are you the second that you are born? 0. In fact, somebody stands there with a stopwatch, and the time you are born is registered, tick. And after 5 minutes, Daddy walks out with the child in his arms to show whoever's watching and says, my baby is how old? 5 minutes old. So I have to have a birthday. So now, if I want to know how old the rock is, how do I know when it was born? Now, if I wasn't there to see it born, sometimes you can be there. If volcanic material comes out of the earth, you can see that it's born kind of now. You know what I mean? But rocks that are supposed to be ancient, I wasn't there, nobody was there. How do I know when they were born? I don't know when they were born. So I have to use a supposition. I have to say that when the rock was born, the clock was set to 0. Now the clock consists of one isotope changing into another. So I must assume that when the rock was born, only the parent isotope was there and none of the daughter isotope. That's 0 reset, isn't that right? Now, is that the case or is it not the case? The answer is that the literature abounds with cases where it is not the case. Where, for example, volcanic ejecta comes out of the rock right now in Hawaii or in New Zealand, and you measure it, send it to the laboratory for dating, and it can measure anything from a few million to hundreds of millions of years old. Now, if that is the case, then is the clock set to 0, yes or no? Obviously not. And if the clock is not set to 0, then how much faith can I have in the dating system? Here's another problem. We are dealing with a closed system. Obviously. If I'm going to determine ratios of one to another, it must be a closed system. Can you imagine, here in the front, I have a timer, a sand timer. You know, like an egg timer? Imagine it standing in the front here. And I turn it, and all the sand is on top, and in the bottom I've got lines indicating the minutes. And after 1 minute, the sand has come down and filled it up to the first line, and I know 1 minute is gone. After another minute, the second line. After a third minute, the third line, etc. That's how the clock works. Now, what if there was a hole in my glass at the bottom? And as the sand came in, some of it escaped from the bottom. Would my clock be accurate, yes or no? No, it would not be accurate. Same with a rock. If I'm dealing with a rock and the elements inside that rock somehow were able to escape a hole in my clock, would I be able to use that sand in there as a time mechanism, yes or no? No. Question. Does lead, for example, dissolve in acid water, in rain? Yes or no? Absolutely. That's why we have heavy metal pollution in our rivers and in our lakes, right? So, if it rains and water falls on the rocks, and the rocks are porous and the water goes through, can I wash out some of the elements, yes or no? Obviously, yes. I mean, that's how mountains work. They soak up the water, and they form huge reservoirs of water because they contain them and soak them up like a sponge. So here are mechanisms of taking out the isotopes. So basically, I cannot guarantee that the decay has been the same. I cannot guarantee that the clock was set to 0 when the material was formed, because it's not set to 0 even today. And I'm not dealing with a closed system, so how good is my clock? Frankly, my clock is useless. Totally useless. The scientific method of determining one isotope relative to the other may be perfect. That may be so. but it means nothing in the light of these points. So when somebody tells me, how old is something? Then how old can it be? As old as you would like it to be. You see, when Einstein couldn't figure out, or the world couldn't figure out, what was happening in terms of light and the movement of light, whether an object was moving towards you or an object was moving away from you, that the speed of light remained the same, although it shouldn't have. It doesn't make any sense. Obviously, if two objects are going to move towards each other, they're going to get there sooner than when they're moving away from each other, right or not? So, what was his solution? He came up with a theory which he called relativity. That's it. So that's the solution to a big problem in science. It's nice, but it's just a word. We don't have to go into all the details. So if somebody asks me, how old is this rock? I say, it's relative. Relative to what? Relative to my paradigm. Relative to my way of thinking. If I believe this rock is young, there is nothing that you can do to prove that it is not. And if you want to believe that rock is very old, there's nothing that I can do to prove that it is not. So believe it if you want to, that it's billions of years old. Or believe it if you want to, that it's a few thousand years old. There is nothing that stops you from believing what you want to believe. Nothing. And no matter how much arm wrestling science does with you, to tell you that you must believe that it's old because that is their paradigm, tell them it's relative. You can believe whatever you want to believe. There is no evidence, impelling evidence to force you to change your mind. You don't have to.